Ladies and gentlemen, please welcome our next discussion on software is eating the automotive world.
Thank you. My name is Jan Becker. I wanted to introduce Apex.AI, our company, and how we work with OEMs worldwide in the automotive space, but also beyond in the larger mobility space. The challenge when it comes to automotive, EVs have now really become the baseline. You don't differentiate anymore through EV and through EV technology. Customers expect EVs, for the most part, really to be digital products with a digital experience much more than a more powerful powertrain or any of the differentiators that mattered for ICE vehicles. And really the basis to differentiate through a digital product is what we call a software-defined vehicle. Now, OEMs struggle quite a bit, especially the traditional OEMs, with the transition from the current ICE products to software-defined vehicles. And Jim Farley, actually lost the monitor here. Jim Farley recently made a quite remarkable interview as the first CEO, stating publicly how much behind the OEMs actually are.
Because they realized that these are digital products, and what will differentiate these products is not going to be, a noise, vibration, or harshness, or bigger engines, or smaller engines, or efficiency. It's going to be software.
Yeah.
We farmed out all the modules that control the vehicles to our suppliers because we could bid them against each other. So Bosch would do the body control module, someone else would do the seat control module, someone else would do the engine control module.
Right.
And we'd have about 150 of these modules with semiconductors all through the car. The problem is the software are all written by, 150 different companies, and they don't talk to each other.
Right.
And so even though it says Ford on the front,
yeah,
I actually have to go to Bosch to get permission to change their seat control software.
Right.
So even if I had a high-speed modem in the vehicle and I had the ability to write their software, it's actually their IP. And I have 150, we call it the loose confederation of software providers, 150 completely different software, programming languages, all the structure of the software is different. It's millions of code, and we can't even understand it all. So, that's why at Ford, we've decided in the second generation product to completely insource the electrical architecture.
Right.
And to do that, you need to write all the software yourself. But just remember, car companies haven't written software like this.
Yeah.
Ever. They've never written software. So we're literally writing how the vehicle operates, the software to operate the vehicle for the first time ever.
Yeah.
So this is actually a very, very concise summary of the state of not just Ford, but really all larger traditional OEMs with respect to the adoption of software and the move towards software-defined vehicles. Now, visualizing that, what Jim said is, we attempted here in this graph. So what you see on the left is really the hardware and software stack, starting with the ECUs at the bottom over the operating system, that's typically QNX or Linux, over the data transport protocols, through a software framework, through the actual application. As you can see here, there are really 150 of these, typically anywhere between 100 and 300, so let's say on average 150 of these ECUs in a vehicle today. And for each ECU, there is a complete vertical integration done by one of the suppliers. And then there are up to, not really 150, but several dozens, up to 50 suppliers providing black boxes, so Ford doesn't know, the OEM doesn't know what's inside, black boxes to the OEM. What the OEM focuses on is really the function specification in the beginning of the design process and the system integration at the end and the whole EE architecture, so how is everything connected to each other. But the core IP is not developed by the OEMs today. It's really developed by the suppliers. Now, what Jim Farley alluded to, where he wants to get to, is this picture. Everything done by the OEM. Now, there are a couple of OEMs that have already attempted this. most notably Volkswagen, Toyota. They started their own software units about 4, 5, 6 years ago. And it's been in the news as to where they are. So Volkswagen recently announced the delay of their own software platform by a few more years, and they now anticipate their own software to come out between 2028 and 2030. What that means in practice, it takes about 8 to 10 years to build a complete software stack for a vehicle, even with partners. So Volkswagen has not been doing that alone, but with partners. So what's the better path forward? Better path forward is really to build and base the software stack on open standards. Even though most OEMs are currently developing, starting at the bottom, are developing their own custom SoCs, they would actually not start, nobody starts, even not Apple for the iPhone, to develop their own chips. They all use the ARM standard. Same for the actual operating system. Everybody uses the POSIX-based operating system. It's either Linux or QNX or one of the other ones like Green Hills. And what we've seen really all across the industry for the data transport and the software framework is the adoption of ROS, the robot operating system, for prototyping. But historically, ROS has really been a prototyping framework coming bottom up through universities and academia. It's not been a production framework at all. And this is actually what we've been working on the past 5 years and what we've released about 2 years ago to the first OEMs. The 2 products that are ROS-based that we've brought to the market are called Apex Grace and Apex.AI. I will talk more about that a little later on. So first, my background, why am I and why are we as a company even qualified to do that? Well, I've been developing exactly this vehicle software, approaching the problem from the software and not from the hardware side for now 26 years actually, so for quite a long time. It actually started with building an autonomous vehicle 25, 26 years ago. This was for Volkswagen automating their endurance testing in Germany. So you can see here going back 25 years ago, there was no electric steering, there was no CAN interface to the powertrain or to the braking system. So we had to build a robot first. You can see that here on the left. We had to build a robot first to sit on the driver's seat, to actually actuate the steering wheel, to actuate the gear shifter here with 3 legs for the 3 pedals. It worked beautifully 25 years ago, but was way too expensive for Volkswagen to then actually even adopt it as a system for a production system for testing. So we built up about a dozen prototypes, but it was overall too expensive for product use. Then I worked for Bosch for a couple of years, developed first versions of adaptive cruise control, stop and go, you see that on the left. Also traffic jam assist, so a level 2 system, today we would call it a level 2 system, 10 years before it became a product and before Tesla launched autopilot. On the left you see a left turn, on the right you see a left turn assist, prevents you from making unintended left turns into oncoming traffic. We developed that prototype in 2005. It launched as a product in the 2017 Audi Q7. And here you see the issue. Very simple level 1 system, 12 years from prototype to product. Translate that to level 3, level 4 system would take us 50 years with the approach the automotive industry has taken so far. So very, very long and slow innovation times. I was then one of the participants in the DARPA Urban Challenge, which was the well-known event DARPA organized in 2004, 5, and 7. I was part of the Stanford team. You see me at the far bottom right with the 2 little kids. That was in 2007. They're now in college. Then I was actually a full-time researcher at Stanford doing the DARPA Urban Challenge since 2010. I'm also part-time faculty teaching, again starting this quarter, on driver assistance and autonomous driving. Then I got involved into ROS, the robot operating system, which started around 2009, really as a bottom-up initiative to develop a robotic framework, which then found a quick adoption also in the automotive world for prototyping, a robotic system to enable robotic and automotive researchers to really collaborate and work on one platform. By the way, AV guys, the monitor here in the front isn't working anymore. So if you could get that fixed, that would be great. This is how Ross started in, thanks. This is how Ross started in March 2010. So those were the first 20, 30 persons developing Ross on these 11 robots. That was called the Pier2, another project that came out of Stanford. I was at Bosch then at the time. We were the first company to contribute open source to Ross. And then we worked on, go back here. We worked on researchy projects like this. So we taught robots how to cook. Today, they're actually burger joints and coffee shops where we have robots making coffee for us. I just visited one in Tokyo the other day. We taught robots how to deliver mail, use power tools made for humans, paint, fold t-shirts. So very researchy tasks that at some point will make it into products, but for the most part haven't yet. Then we started to look at product development. So we developed software for this robotic lawnmower, which launched, I think, in Europe in 2013 or 2014. Very successful there, unfortunately not sold in the US. We also spun out a company, Mayfield Robotics, to address robotic interaction, sort of as a companion. Unfortunately, that company shut down a couple of years ago. Then we started to look into agriculture, a big market for us again today, where we developed this robot, also running on Ross, to do organic farming. So we could separate wheat from plants and then manually destroy the wheat without using pesticides. And then we started in 2011 to also use Ross in autonomous driving. This was the first vehicle we built up back then. Second one, then a couple of years later. Then I left Bosch in 2015, joined Faraday Future, a company in LA, also developing electric software-defined vehicles where we also used Ross for autonomous driving. This was a CES 2017 demo where we showed driverless parking. And really what I had learned around those 10 years using Ross in robotics and agriculture and autonomous driving is we used it at Bosch intensively. A lot of companies, for instance, including BMW, used Ross for prototyping, but everybody got stuck taking it from a prototype into a product. And then I founded Apex.AI in 2017 to address exactly that. We took Ross, we made it robust, reliable, and we've taken it in the meantime through automotive safety certification. We are funded by Silicon Valley venture capital firms, so Lightspeed, Canaan, but then also quickly received a lot of interest from the automotive companies. So Toyota invested, Airbus invested. You can see that shows the applicability not just for cars, but also for flying vehicles, so drones and eVTOLs and planes. And then all the suppliers, so Hella, Jaguar Land Rover, Volvo as a truck OEM, so Volvo Group, the suppliers, ZF, Conti, agriculture company Echo, and most recently Daimler Truck invested, and we are working with most of them also on the product side. In the meantime, we've expanded from Palo Alto to Germany with 3 offices in Stuttgart, Munich, and Berlin. About a year ago to Sweden, and most recently we have sales offices in Tokyo, open sales offices in Tokyo and in Seoul. Coming back to Ross. Ross, since its inception in around March 2010, has become by far the most popular software framework for robotic, automotive, and mobility applications. There are tens of millions of downloads every year. There are hundreds of thousands of users. It's open source. You don't have to register, so you can just download it. So there are probably millions of users, but the actual numbers are known. There are counted almost 1,000, probably way more, companies that use Ross in development and in the meantime also in products, including, as you can see here, pretty much all the car companies. So what does Ross do for you as a developer, as a company? So when I started, I alluded to that earlier, when I started my career 20 years ago, there was basically 3 times the redevelopment of every idea. When we developed the traffic jam assist or the left turn assist, it was once developed to a prototype, proof of concept stage, in corporate research. That took typically 3 years. Then it was handed over to a product department. Of course, they redeveloped it from scratch using a different implementation. That was used to show the product idea to customers. Then once the customer comes and signs a contract, then there is the actual product development. Each takes about 3 years, maybe 4. That times 3 is 12 years of innovation time. So painfully slow and absolutely not competitive in today's world. With ROS, came out around 2010, the proof of concept phase was cut down from what took us about 3 years to a couple of weeks. Because all the base software, the framework is already there, you can really focus on developing the application. But because ROS at the time wasn't and isn't product ready, then for the prototype and the product stage, again, you go through these 3-4 year cycles. With ROS 2, that came out around 2017. Also, the prototype phase got shrunk down significantly because ROS 2 was designed to run on embedded systems, supports a lot of the automotive protocols, but still it isn't real time, it isn't certified, it isn't robust enough to run into a product. This is exactly what we addressed now. Being ROS and ROS 2 compatible, what we addressed here at Apex.AI. So what we are focusing on, we see ourselves as a company improving, accelerating user experience. And the users for us are the software developers. Software developers are rare, hard to get, expensive, so making them efficient saves our customers, the car companies, the mobility companies, not just time to market, but also a lot of money. We see, compared to the competitive products like Adaptive AutoSAR, like AutoSAR Classic, or some other frameworks, we see developer teams shrink by up to a factor of 10 when companies adopt our software. So superior user experience. And again, the user is the developer. We introduce often with our customers state-of-the-art software development processes and tools. You can't imagine sometimes how outdated and slow and inefficient the tool chains and the development processes are that OEMs still use today. Very important is development with a clean architecture without silos on the development phase. You saw that in the initial picture that also Jim Farley described, basically having 150 silos across the software in a vehicle. Because software for each ECU is developed in a silo separately by a supplier not talking to the other supplier. So those silos have to be removed, have to be broken. Everybody needs to work on one set of APIs that are common across the whole vehicle. And this is what OEMs are introducing today. Very important, once you have access to all the source code, everybody works on one set of APIs, is continuous integration and continuous testing and deployment around the whole development lifecycle. I'll come to that in a bit. And what you see in vehicles today often is safety and security is not considered from the beginning often because there is a lot of legacy software in vehicles today, sometimes software that has been carried over for generations, and then safety and security is patched on top, but is not considered throughout the whole development process from the beginning. This is actually very comparable to what we saw in the IT and the cell phone industry about 15 years ago. About 20 years ago, I had one of these Nokia phones. Then in 2007, I had just moved to Stanford. The first iPhone came out. And with the iPhone, actually a couple of years later, not from the beginning, with the iPhone came not the App Store first, but came a software development kit called iOS SDK, which provides all the base software that is common to all apps, made by Apple, provided to the developers. So no developer for an iPhone app has to deal with how to get data from the internet, how to access a speaker, how to open up a virtual keyboard. So all the functionality that is common to most or all apps is implemented and abstracted in that SDK. Conceptually, that's exactly what we provide to the automotive industry now with Apex Grace and Apex.AI. An SDK which implements all the functionality. How do processes communicate with each other? How do processes communicate across ECUs? How do developers start and run processes such that they are safe, secure, reliable, and run in real time, and do not interfere or get interfered by through other processes. So that is all abstracted, and the application developer, which should focus on the application they're developing, like localization, path planning, autonomous driving, ACC, emergency braking, whatever. They focus on the application and not on making it real-time reliable, safe, and secure anymore. That's all abstracted away. So the way we've done that is we've taken ROS, we kicked everything out that is not needed for automotive, we rewrote most of it with real-time and determinism in mind. Then we certified it with the TÜV Nord in Germany, so one of the functional safety assessors, to ISO 26262 ASIL-D, which is the highest level of safety described by the ISO standard. And that has then been released since March 2021 as Apex.AI cert. Should I go back? Do you want to take a photo? All right. This is a V-cycle. Basically the process that describes typical automotive development today. So you start on the left top of the V, describing the vehicle and the requirements the vehicle should fulfill. Then it goes down, breaking the requirements up onto the system level and the subsystem level and the module level. Then the actual implementation happens at the bottom of the V, and then you go up, do verification, validation, ultimately integration into the vehicle. A lot of people say the V-cycle is great, but it doesn't work for agile development. That is actually not the case. The model is still valid, but there's another issue with the V-cycle. It's actually not one V-cycle, but if you remember the picture Jim Farley painted, which I tried to illustrate on one of the first slides, there's actually not one V-cycle, there are 150 V-cycles. Every supplier does their own V-cycle. And there is no real integration and verification and validation until you hit the very top of the V, the right top of the V, which here is called vehicle test and integration. So the result is the integration happens very late, so all the issues are discovered at the very end of the process. And then the vehicle is already developed, and then you have to go back to the top left, and then you have to fix all the stuff again. And that then takes months to years. So the reason is, 150 suppliers, they don't talk to each other, and they don't work on the same software platform. And this is what the OEMs have to change. So they really have to bring it back to one V. Then you can work on a V-cycle again, and then you can iterate in the V-cycle as fast as in a day. I will show that in a minute. Another way to look at it is through the development workflow. So basically breaking up the V, putting it into one flat line. So you have the system design and the network design done by the OEM. Then in today's workflow, OEM calls up to 150 suppliers. They all work on their submodule. That takes a couple of years. Then they come back, and then the OEM does the integration. There are actually three major issues with the workflow today. The first one is the system design is essentially done on a whiteboard, disconnected from the implementation and disconnected from the software, from the coding. So you don't notice if something is wrong, because it's just on a logical design, not an implemented design. Then, as Jim Farley also pointed out, the implementation is done completely by the suppliers, meaning there's no OEM involvement, no IP is owned by the OEM, which also means the OEM can't fix things. And then the third issue, I pointed that out before, is the late integration. So you don't notice what's wrong until you're at the end of the development cycle. And then you have typical update cycles of, and I'm not joking here, of 6 to 12 months. Because you have to go back to all the suppliers involved and to whatever needs to be changed. OEMs have to place a change order that gets negotiated, goes through purchasing, then goes to implementation, then goes through verification, validation on the supplier side, then goes back to the OEM, then needs to be integrated and validated again. And 9 months is actually not uncommon at all. The new OEMs, and we see that actually a lot in China, where OEMs have started sub-brands. specifically for the electric vehicles, with no legacy, development workflow set up from scratch, software bases set up from scratch. And some of our customers have now started both on the automotive but also non-automotive, so off-road agriculture or commercial vehicle side, have implemented a workflow like this. Tesla has done that pretty much from the early days. System design, network design, implementation with partners, but implementation is completely owned by the OEM. And then you get to update cycles of a day. Because you have all the software in-house, you have a change request, you implement it yourself, you run it through your CI/CD several times a day. You have a complete vehicle software up and running if you want to every day. So typical update cycles are then anywhere between 7 and 14 days, opposed to 9 months. A simple example here is Tesla launched a function called, I think it was called dock mode a couple of years ago. Essentially, you have a dock in the car, you press a button, your AC starts running even though you leave the vehicle. At the same time, a dock is shown on the center console display, letting persons outside of the vehicle know there's a dock inside, the AC is running, there's no danger, you don't have to break into the car and get the dog or baby or whatever out. Tesla, synonymously for an OEM with an agile development workflow, can implement and launch such a function within a week or two. A conventional OEM cannot, because they first have to go to the climate control and AC vendor, they have to get that software changed, then they have to go to the manufacturer of the center console display, and the respective control unit and the software have to get the image of the dock implemented, and that takes, again, anywhere between 6 and 12 months. An EV manufacturer with an agile workflow can launch a function like that in a week or two. That's the practical difference for the end consumer. So how to transition from a conventional workflow and set up to a modern, agile software project. So we've done a number of projects like this with both small and large automotive and non-automotive companies. And what we found what works best is starting with a really small team. Typically 5, 6, 7 persons from our side, 5, 6, 7 persons from the OEM, from the customer. And first we decide on which environment do we use, which EE architecture do we use, which ECU, so which hardware, which software framework, whether it's ours or somebody else's. What do we use for system modeling? How and where do we use CI/CD? So a very small team very efficiently decides on these core features, on the core setup. Then we start to add, how do we do over-the-air update? How do we run and scale to the cloud? Which processes do we use for functional safety? We start to consider the SIL, HIL, WIL setups, and so on and so on. Then and only then, that's typically another 3 to 6 months. Then and only then, we add the function developers. Because then, the basic environment, the base software is stable, APIs don't change anymore, and then the function developers can get up and running quickly and are productive from day one. What we see in projects that ultimately fail, functions developers start first, then APIs change for another year or two, and function developers, instead of focusing on the function development, run behind changing APIs, run behind changing hardware, run behind changing cloud providers or whatnot. So first put the basis in place and then start with the function development. So our offering on the SDK side is once, we call that Apex Grace. It's really automotive grade ROS, safety certified to ASIL-D. And we have that in the market since 2021 now. The second product, which we've launched recently, and which is currently in the process of being certified, is Apex.AI. That is, to our knowledge, the first product worldwide that integrates all the automotive communication protocols into one software with one application-facing API, which also means if you move software components between different ECUs or between different cores or SoCs on one ECU, the APIs don't change. The protocol underneath that is being used may change, but the application-facing API doesn't change. So what we've integrated specifically is zero-copy communication, so very low constant latency, independent of the data size, communication within one memory space, so on one ECU. A DDS is implemented, some IP is implemented for cloud communication, a WebRTC and MQTT is implemented, again with one application-facing API. We have customers today running, for instance, interior monitoring for ride share and ride pooling using our software. We announced it recently, it's Volkswagen Moya. They use that software for communication to the cloud and to the backend as well. So from a software stack perspective, that looks like this. You run in a vehicle, you run on an SoC. We are actually SoC hardware agnostic, so we can run on ARM, Intel, NVIDIA, Qualcomm, TI, whatever the hardware provider is. We are also operating system agnostic, so we work with QNX, Green Hills, PikeOS, Integrity, Linux, and so on. So operating system of your choice, really as long as it's POSIX compliant. And then Apex Grace and Apex.AI sit on top. This is how we started about 2 years ago going to the market, specifically for microcontrollers and for large SoCs. And we have customers running all sorts of applications on top. So from ADAS over autonomous, powertrain, telematics, interior monitoring, both in in passenger cars, trucks, agriculture, and so on. What we've worked on more recently is extending that into the cloud. What's still work in progress is elastic computing, so shifting workload between the vehicle and the cloud. What we've also implemented and launched successfully to customers, so a lot of our customers adopt that as a continuous development workflow. That looks like this. So we have developers, both on the OEM side, on the, for instance, partner supplier side, on the hardware BSP component provider, so that's typically the SoC vendor. They all work continuously. Software gets uploaded, so developed, uploaded into the cloud, automatically integrated into one image. That automatically gets deployed into a device farm. We have a large device farm in our office, so being tested constantly on all the different hardware, all the different customers, both commodity and custom hardware. Then that process automatically builds a validated software image that then gets through the repository over an MQTT bridge deployed into the vehicle. Then customer vehicles, OEM vehicles are constantly driving around being tested. Software test results get recorded into a database. Within minutes to hours, the test results get through the cloud again, get to the developers. Developers can look at the results, implement it. That cycle runs up to a couple of times a day, so customers can iterate quickly, implement, look at results, implement, get tested. So we have up to 4 times a day customers that run through that cycle. Very efficiently, very agile, still using the V process. What we've also worked on is integration of microcontrollers. We announced that about half a year ago at Embedded World. We have a partnership with Infineon, where their Aurix safety controller, also ASIL-D certified hardware, has been integrated with Apex Grace and Apex.AI. You can now program both microcontroller and microprocessor using one ROS-based API very efficiently. With that, as I said, we have deployments in the passenger car industry, in the commercial vehicle industry, in trucking and agriculture. We just announced Krone Lemken as a customer. We have customers in the marine industry. We haven't announced yet, but will announce soon. We have aerospace customers. We have robotics customers. So it's very, very widely and broadly applicable. With that, thank you very much. And I think we have 9 minutes left for questions if you have any. Thank you. Any questions? Oh, there's one in the back. Oh, there's a microphone behind you.
Are you able to speak on who some of your aerospace customers are? Or
Not yet, no, but hopefully soon. But thanks for asking.
Sure.
But maybe in a more general space, so one of our investors is Airbus, and applicability is really there where manufacturers start with ROS or some more agile framework, opposed to the large passenger planes where you really tackle the problem of reliability through massive redundancy. So they typically have five computers by different manufacturers, and that is proven software that is unlikely to change. But when weight is a factor, when power consumption is a factor, that's where our software is beneficial.
I'm wondering about the difference between like an infotainment center update versus like a critical safety.
Can you say it one more time?
You're talking about speeding up the development
Yep.
cycle, and I'm thinking about updates for the infotainment center versus updates for an ADAS safety critical feature. Are those sort of on the same timeline with the technology you're developing, or are they still different?
You mean you're asking with respect to the frequency of updates?
Yeah, the
Okay.
whole update.
So the question was, do infotainment software and ADAS, AD software differ in terms of frequency of updates? So conceptually, no. In practice, infotainment is usually updated more often simply because consumers expect an iPhone-like, app-like feature where you get updates every couple of days. And modern infotainment solutions in cars typically implemented on top of Google Automotive. I showed that earlier but didn't point it out specifically. We also have an integration with Android Automotive running in most infotainment systems today. Those are generally updated more often, or simply because there are also more features that can be updated, consumer-facing features. On the ADAS AD side, it's mostly enhanced functionality, sometimes also map updates. They can be as often, but in practice they're typically not. Anybody else? Oh, it doesn't seem like us again. Thank you very much. Hope you enjoyed it.